All right, so I'll back up a little bit because I just started the recording. We're going to talk about equilibrium, and we're going to use this oxidation of glucose the chemist's way. It starts as a solid. We add oxygen. Remember, this type of reaction, which is a combustion, when you react with oxygen. Anytime you take a compound and react it with oxygen, it's in a class called combustions. And remember, the classes of reactions, they can overlap. So this is a balanced equation of the combustion of glucose in oxygen. And we want to write the equilibrium expression for this reaction. Now, what you would typically think is the expression would be reactants over products. Right? So we would normally write it like this, with that power, and this with that power, and this with a single power, and oxygen with that power. But then you ask yourself, does that obey the rules? And the answer is no. Because solids and pure liquids are left out of equilibrium expressions. The reason being that in an equilibrium situation, their concentration does not change. If it's a pure liquid and a solid, you can add to or subtract from, but their concentration does not change. So we have to, oh, Kessa. Let's get everybody marked in here. So I've got Kessa and I've got Heather. So far, that's it. Okay. So this expression is not correct because we've included a solid and a liquid, pure liquid. So the correct expression would be only the gases. We don't have any aqueous solution involved here. So the only thing left is gases which do change in concentration as the reaction proceeds, reaches equilibrium. So that would be the equilibrium expression for that reaction. Now, this is also in terms of molarity. That's what the square brackets mean. This is concentration, and you can express gases in terms of molarities, moles per liter of space. Right? So you'd have a liter of space container, and you would have so many moles of each gas in it. But typically what we do, if the reaction only involves gases, we want to express it in terms of partial pressure because that's easier to measure. So if we were to take this, which would be designated equilibrium, and we want to convert that to the K in terms of partial pressures, we need an expression that will give us that equivalence. Okay? So that's the relationship. The KEQ and the KP are not identical in units of measure or in magnitude, but they are related. We just need the temperature in Kelvin, whatever the temperature happens to be. And if you're not told, you just assume it's standard temperature, which is 25 C or 298 Kelvin. And the R is going to be the one that has a pressure term in it. So that's the one with atmospheres, liter atmospheres per mole K, which would be 0.08206. Okay? And that will get rid of, let's see, moles and liters and temperature Ks and leave us with atmospheres. Or it might leave us with no atmospheres, right? I mean, the convention is that the Ks never have units assigned to them because they can get too complicated. But if we want to look at this one and just say, what would the units be for this one? If we were speaking in terms of Kp and instead used partial pressures, that would be in atmospheres. And that would be atmospheres to the 6th power divided by atmospheres to the 6th power. The K would be a dimensionless number in this case. It had no dimensions. The only way we'd know that it's derived from partial pressures is designation of K sub P. Well, for that matter, KEQ would be dimensionless also because molarity divided by molarity is nothing. Right? So if you don't specify what type of K it is, in this special case, you could mistake one value for the other and you'd be wrong. Okay, so we've talked about the relationship here, K and R, what it is, and temperature, what it is. What's delta N? Delta N is the change in moles of gas. That only has meaning for a Kp, where the moles of gas do influence the pressure. Well, according to Avogadro anyway. So what is delta N? Well, how do the number of moles change in the balanced reaction? Right? So here you go from 6 moles of oxygen to 6 moles of CO2. Right? What's the change? 0. 6 minus 6 is 0. So this would be, in our case, 0, which would make what? Anything to the 0 power is 1, right? So in this special case, Kp and Keq are equal numerically. That's just a fluke. It happens sometimes. But don't lean on it forever because it doesn't hold true for every reaction. Only where you have this special case, right, where the number of moles are the same, the number of moles of gas on the same on either side. Now, if we had different gases up here and the total number of moles were the same here as here in the products, then you'd still get a delta N of equal to 0. Delta N's can be positive, delta N's can be negative. Right? We know the number of moles of gas in some reactions goes down, in some it goes up. Like nitroglycerin, it goes up to like 24 times as much gas on the reactant side, on the product side, as on the reactant side. That's why it serves so well as an explosive. And then there are other reactions where the concentration of gas goes down. Okay, so that's sort of a bird's eye view of equilibrium and reminder of the rules and how to produce an equilibrium expression for a balanced equation. All right. So let me see what's next on the agenda. Let me skip over to, just for a second, oxidation reduction reaction. And let's just be sure that we're confident in identifying the oxidation phase and the reduction phase of a given reaction. Okay? So let's say we have the manganate ion, and this is going to be a net equation, right? Most oxidation reduction reactions, well, not most, I say some, are best studied as net reactions. So the The spectator ions, just leave them out because they just muddy the waters. They don't change. Their oxidation states don't change. So they don't need to be there as long as we balance the equation correctly. So let's try this one. Let's see, let me move down here and give me some headroom. See, can we see that? Yeah, it's visible. And this is the oxalate ion. It's 2 minus. Yeah, 2 minus. And 4 hydroxyls. So what does that mean? That means this reaction is carried out in basic solution because it has hydroxyls there. And let's see. Let me just move down here for the products because this is a big reaction. Manganese dioxide, solid. Is one product. And carbonate ion is another product. And the last one is water. Okay. Now let's just say you were given that balanced equation, and for test-taking purposes, you're guaranteed it is balanced. If you don't believe it, just check it out. 2 manganese, 2 manganese, 6 carbon, 6 carbon, hydrogens, oxygens. Let's do oxygen. 8 plus 12, is that right? 8 plus 12 is 20. 24 oxygens. Let's see, 4 plus 18 is 22, plus 2 is 24. So we're balanced. Now the question is, how do the oxidation states change for this reaction? Well, some of them change and some of them don't. Unless you have specific reason for oxygen to change, you assume that it's a 2 minus oxidation state. Example where it might change. Let's see. If you either have a reactant or a product as elemental oxygen, O2, and somewhere else in the equation, if O2 is on the product side, then the reactant side might have oxygen in a compound. That definitely has changed oxidation state. So in that case, the oxygen, elemental oxygen, O2, would be 0. And the oxygen on the other side is more than likely 2 minus. But in this case, all of our oxygens are in compounds. We can assume that they're 2 minus. So that helps us determine oxidation states for all the rest of the elements. So let's see, what would manganese be? Well, if we got 4 times 2 minus is 8 minus. We have to hold one out for that charge. So that makes manganese has to be 7 plus to balance those other 7. Okay, so that takes care of manganese on the reactant side. How about carbon? Well, 4 times 2 minus is 8 minus. And we have to hold 2 minuses out. So that means we only need to balance 6 minuses with 2 carbons. So each carbon, both carbons together would be 6 plus. So each carbon would be 3 plus. Okay. Hydroxyls are always 2 minus for oxygen and 1 plus for hydrogen. And all you have to do is say 2 minus and 1 positive yields what charge? 1 minus. How about this manganese? 2 times 2 minus is 4 minus. It's a neutral compound, so manganese has to balance all 4 minuses by itself. 4 pluses. Okay. How about this carbon? 3 times 2 minus is 6 minus. And 2 minuses have to be held out for that charge. So carbon only has to balance 4 minuses, which makes it 4 pluses. Okay. And on this side, same thing. Oxygen is 2 minus, hydrogen is 1 plus. Add them up, and you get a neutral compound. So we're good there. So what have changes taken place? Well, we've gone from manganese 7 plus to manganese 4 plus, which means what? Oxidation or reduction. Or rig. Oxidation is loss. Reduction is gain. We had to gain 3 electrons to go from 7 plus to 4 minus. So we have a gain of 3 electrons per manganese. Okay. Carbons. Carbon went from 3 plus to 4 plus. So it had to lose 1 electron per carbon. So that's a loss of 1 electron per carbon. Now, do the number of electrons balance in this reaction? How many electrons are part of this change for this manganese? Well, there are 2 manganese here and here, so that means we had 6 electrons gained in the reaction. How about this one? We have 6 carbons, right? 6 here, 6 there. 1 electron per carbon times 6 carbons is 6 electrons lost. Okay, so if we were to, if we wanted to write this reaction as independent oxidation reduction reactions, and for instance, if we wanted to create a battery using this oxidation reaction, we'd have to know which half cell is which. So the anode is where oxidation takes place. So we would conduct the oxidation reaction here. Oil, oxidation is lost. That would go in 1 half cell, the anode on the left by convention. And this would go on the product, on the cathode side for gain. Now, how do we know where these go? I mean, where hydroxide, because this is an overall reaction balanced. We would have to take those anode and cathode half reactions and go through the process of balancing them independently before combination. And once you've reached the stage where you balance the electrons, before you combine the reactions in the final, then you would have those 2 half reactions set apart. The anode, the loss of electrons, this one would go in the anode with its balanced half reaction, and the half reaction for the gain would go in the cathode side. Then you would be able to go to your chart, your standard reduction potential chart, find those half reactions, and calculate a standard potential. Okay? All right, so I don't want to waste too much time doing that. That's just the way it would have to be done. Okay, let me see what else looks interesting here. Okay, let's say we have, we're going to talk about Le Chatelier again. Okay, so what things can change in a reaction that will produce an imbalance in equilibrium and thus a shift. What would be a stress to the system? Well, it depends on the reaction, right? Say you have okay. Now, if we're simply talking about, let's just say, okay, hypothetically, let's say they're all solids. Well, maybe there's a liquid, pure liquid, and there's a solid. Right? And you add some D to this reaction. What's going to happen? I'll just think about it for a second. Okay, the answer? Nothing. Nothing will happen. Why? Because you did not change concentration. Adding solid doesn't change concentration. It's still solid. We could do the same thing with liquid, or subtract one from either side. It still wouldn't shift the reaction. All right. So suppose we had, and let's say aqueous here, gas here, and solid here. Okay? These are two aqueous solutions, and when they're combined, they produce a precipitate, solid, plus they evolve some gas. Okay? That can and does happen. So let's say, what's going to happen if we add some B? How will the system react? Add some B, you shift that way. Why? Because this increases the concentration. It'll produce more gas and more solid. If you subtract some B, you get a shift this way, because you decrease the concentration of B. And then the response is to move back to that side to mitigate the imbalance. Okay, so that's concentration. We talked about concentration changes. That's a good place to start because it's easy to understand. Now let's talk about gases. If you've got a gas involved, what happens if you increase the volume? Okay, what happens when you increase the volume? You make more space in the reaction vessel, so the system tries to compensate by pumping more gas into that space. And by increasing the volume, you also decrease the pressure. If you decrease the pressure, then the impacts, using the kinetic molecular theory, the impacts of this gas with that solid, which would cause a reverse reaction, are decreased. You don't have as many impacts. So the reaction rate decreases. If the reaction rate decreases, then the system is going to try to compensate by increasing the amount of that gas in the space until the equilibrium is established again. So if you increase the volume, the system will shift toward producing more of that gas. Now this is a simple case where there's only one gas involved. So you can understand change in volume and pressure. Let's suppose, though, that we have gas on both sides. And let's just say, for argument's sake, this is no longer a solid. Let's just say it's aqueous now. And we have a gas on this side. Now, of course, if you add C, it's going to go back this way. If you add B, it's going to go that way. You subtract C, it's going to go this way. Subtract B, it's going to go that way. But suppose we don't do that. Suppose we do change the volume. This time we're going to increase the volume. I mean, decrease the volume, increase the pressure on this system. How will the system react? We don't know. We're not given enough information because we don't know the ratio of those two gases, how many moles there are on either side. All right, so let's give you some more information. Let's say this side produces 3 moles of gas, this side 2. All right. Now, if you increase the pressure, decrease the volume, the system is going to react to reduce the amount of gas in the space. It's got too many molecules in there. So when you increase the concentration of the gas molecules, the gas tries to compensate, the system compensates by removing some of those gas molecules because it has less space for them now. So which way would it move to do that? It would have to go from 3 down to 2. Okay? Now, the other one we discussed was heat, right? Temperature. So what effect does temperature have? Well, ideally, and we don't even need to know that information now. Well, yeah, we could. Let's go back to where it was. Aqueous, gas, gas, aqueous. Okay. Now, how do we know the effect of temperature? You need to know, is your reaction endothermic or exothermic? So if it's exothermic, the heat that's involved in the reaction is a product, right? Because it gets warmer. So that's an exothermic reaction. Now you can make a prediction about changing the temperature. If we increase the temperature, we're adding to the product side. So the system will shift back to reactants. If we remove some of that heat, right? If we refrigerate the vessel, and as the heat is produced, we remove the heat, then it's going to continue shifting this way, trying to reach equilibrium. If it's an endothermic reaction, the heat involved in the reaction is a reactant. So now if you increase the temperature, you're going to increase the amount of product. So we increase the temperature, make more product. If we decrease the temperature, we shift back to reactants. Okay. If you're not given the the heat signature of the reaction, is it exothermic or endothermic, then it may require some assumptions to be made, right? If I take a compound, a solid, and everything on the product side is gases, I'm pretty sure that that's exothermic, right? Because all the energy that was stored in those bonds is now released on that side. Example is your nitroglycerin. There's no guarantee, but if you have to make assumptions, then you can also, if you're given the compounds, you can estimate the delta H by looking at the bond energies. Remember how to do that? You take the bond energies times the number of moles of each bond on the product side and subtract the bond energies on the reactant side. And that will give you an estimate of the delta H. I think we did I don't think did we do that this semester? It might have been first semester.
I think it was this semester.
Was? Okay.
I think.
Kind of get blurry. But you can make that estimate. If you're actually given the compounds and it's a balanced equation, then you can estimate the delta H and answer the question. But just a reminder, the exam coming up is an ACS standardized exam. Well, it's derived from. So the questions are not going to be that complex, right? Because they're multiple choice and they want you to be able to bam, bam, bam. You may have to make some calculations, yes, but they're not complicated ones. Oh, one other thing. Suppose in our reaction, we have something that goes here, and it comes out there. Now, if we increase the amount of that one, what happens to the reaction? Nothing. If it goes in on one side and comes out unchanged on the other side, it's a catalyst. Has no effect on the equilibrium. Only affects the rate. All right, so let's take that one and jump to, let me see. Here we go. Let's take a look at this one. Stream of consciousness here. Suppose we have a reaction mechanism. And the net reaction is ozone plus the oxygen radical. And it produces 2 oxygens. Now, on the surface of the Earth, that's a good thing because ozone is toxic and radicals are too, but not very common, but ozone is more common. So if we can get it to react with radicals, we can produce oxygen and then we can breathe it. But in the upper atmosphere, it's bad because we want this one in the upper atmosphere. Why? Because it is very effective at absorbing certain wavelengths in the UV spectrum. And that protects us here on the Earth's surface from the ionizing properties of UV. But that's the overall reaction. And we proposed steps in the reaction. This is a 2-step reaction. And the first step is L, ClO plus. All right, so there's one of our oxygens product. Means we probably have another one down here. So then we have ClO plus O, I think. Yeah, produces Cl plus 2. Okay. So the question is, where's the catalyst? What is the catalyst in this reaction? Well, when you have this type of information, you look at your steps for something that is down here, is not up there. And then you also look at one that comes in as a reactant in the first step and goes out as a product in subsequent steps. If there are more than one, it could come out at any place. So where is that? Well, let's see. Chlorine's not there, right? Chlorine oxide is not there either. Right? But which one's the catalyst? The one that goes in as a reactant and comes out as a product. That's the catalyst for this reaction. Now, these are all gases. And we didn't tell you, but all of those are gases too. So what type of catalyst is this? It's a homogeneous catalyst. It's in the same phase as the reactants and products. Actually, it only has to be reactants. Same phase as the reactants. So it's homogeneous catalyst. Okay, while we're here, what is CLO? As an intermediate. It shows up and disappears before the end of the reaction. It's an intermediate species. Okay. And how do catalysts work? Since we're on that topic. How does the catalyst increase the rate of reaction? Right? Remember this diagram? Let's see, progress. Now let's see, reaction progress. Okay, goes this way. And this way is energy. Total energy of everything at that level. So let's say we start off down here. Go that. And that. Okay? Let's identify places on this diagram. What do we have over here? We have reactants. Over here we have products. Here we have an intermediate, sometimes called an activated complex. Okay, so what's the activation energy for this reaction? Right? It's the difference between energy of all the reactants together, the difference between this energy level and that energy level. All right. Let's see, what else can we determine from this reaction? The difference between reactants and products. As long as the pressure and temperature are constant. That's true. Okay. Oh, I know where I was headed now. Catalyst. So what would the catalyst diagram look like? Well, if it's a bona fide catalyst for this reaction, the activation energy is decreased. So we would get a different curve. Let's say, just for argument's sake, it went up here like this. Like that. So this is the activation energy for the uncatalyzed reaction. And this right here is the activation energy for the catalyzed reaction. So what does that mean for reaction rates? Well, all things being equal, same temperature, same pressures and everything, the amount of energy required to reach an activated complex and move to products is much lower. So you have more energy available at a given temperature for those impacts that will produce products. So remember what's required based on the kinetic molecular theory. What's required for a reaction to proceed? You have to have enough energy, whether it's catalyzed or not. You got to have enough energy And you have to, well, excuse me, first step, you have to have an impact. The reactants have to meet if there are two of them. If there are one of them, of course, then you can skip that step. But if there are two or more, they have to impact. And they have to impact with sufficient energy to reach the activated complex. And then the third is orientation. They have to be oriented correctly, because during a reaction, you have to break bonds and make bonds. So you have to orient correctly so that you break the right bonds and you're in a position to form the bonds you want. So those three are required. So let's look at that in terms of catalyst. Where does the catalyst come in? Well, it doesn't affect the impacts. You've got the same number of impacts as before. But now, more of the impacts are at the right energy to produce the reaction. Orientation is a wash too, before and after. They're oriented the same. That's not true. Why do I say that? For homogeneous systems, orientation's not significantly different before and after catalyst. But for heterogeneous catalysts, orientation does matter. I'll just make this quick. Say you're in your catalytic converter in your engine, and you're small enough you can see the surface of the beads with a platinum and let's see what else. Platinum and maybe some palladium. Yeah, those are two common metals on the surface of your ceramic beads. What are those? How do those catalysts work? As your gas passes over it, the gases adsorb to the surface. I didn't say absorb, I say adsorb. Adsorb is with a D. Only happens on surfaces. So they attach themselves temporarily to the surface of the catalyst. And then another gas comes along that is of sufficient energy, and it plops down right next to the other one. So you have A plop down on your catalyst, your platinum palladium catalyst, and then B plops down right next to it. Now they're oriented properly, and they have enough energy because they're still vibrating. So the bonds break, new bonds are formed, and then the product, whatever it might be, is released. So in that case, in heterogeneous catalyst systems, the orientation does matter. Everything taken together can be expressed in terms, in simple terms. A catalyst provides an alternate pathway for the reaction to proceed. And that alternate pathway gives you differences here. Okay. To make a long story short, all right, let's see how we're doing. Okay, time is still good, but that won't last forever. So let me get my horse in gear, and let's see. Okay, we were talking about mechanisms, so let's talk about mechanisms a little bit more. Let's try this one. NO2, CO2. Step one. This is a two-step reaction. And it yields, let's say, ClNO2 and Cl. 2. Okay. Now we're going to tell you something about the steps in terms of rates. This is the slow step. Okay. Step 2 is NO2 plus Cl yields ClNO2. Okay. So the chlorine atom here is an intermediate. If we add these together, this is the fast step relative to the other one. And if we add those two together, right, that one cancels and that one cancels. We get two NO2s and a Cl2. Yep. And that yields 2 ClNO2. So that's the overall reaction. Now, what would be our rate expression for this reaction? The differential rate equation would be the rate equals something. It is a K value times the concentration of NO2 to some value, its order, and then Cl2 to its order. Let's see. Yeah. Okay. Now, this is the type of problem that showed up in the PowerPoints that was a bear to solve. It was not obvious from the information what the orders were. We had to do some finagling, as we say in the South. But in this case, we have a clear-cut way of finding the orders from the steps. Why? Because this one and that one both occur in the slow step. Right? The slow step determines the order based on its coefficients. I know in the overall reaction, you can't use coefficients to determine the order, right? If that were true, then this would be 2 and that would be 1. It doesn't work that way. But if you do have a valid mechanism proposed, and you've identified the slowest step, that is the bottleneck, that determines the overall rate. Then you can go to that equation, and it tells you what M and N are in this case, right? Coefficient here is 1, coefficient there is 1. What does that mean actually? In terms of the molecular level of activity, it tells you the molecularity of the reaction. The molecularity in terms of NO2 is 1. Molecularity in terms of CO2 is 1. Or you can leave those out because it's understood. Now, what's the overall molecularity of this step? Is 2, because you have 2 molecules coming together at once to react. Even though another NO2 comes along later, the rate determining step is this one. And that gives you information about the rate. Now, you can compare that with actual experimental determination of the order of each one. And actually, that's the way that you help tease out whether or not this is a valid proposed mechanism, right? Because remember, mechanisms, you sort of shotgun. You just put all possible reactants you can think of, blast them against the wall, and try to line them up. And you propose various mechanisms. You know, could be 3 or 4, it could be 24. And then you go down through them and you start lining them off. Says that's stupid, that can't happen, that can't happen, until you get down to a smaller amount. And then when you do actually determine the order of the reaction, it gives you a clue as to whether your proposed mechanism is valid. Okay. Can't think of anything more to say about that one. So let's see about oh, okay. We can go back to colligative properties for a second. All right. So what's a colligative property? It's a property of a substance, or it's a property of its behavior that does not depend upon intrinsic property of the atom or molecule. To put that another way, by example would be best.
Is this the Raoult's law or whatever? I don't know how to say that name. R-A-O. Raoult? Yeah.
Raoult's law. No, Raoult's law is you're gonna stump the band here. Let me see if I put it in the useful information. Raoult's law should be.
I just didn't know if it was among like the same concept with that definition.
No. Hold on a second. I got to refresh my memory.
I'm sorry.
That's all right. I haven't studied for my own exam yet. So let me see if I can get my synapses firing here.
I think I'm getting confused. I think Raoult's law is based on pressure with the colligative theory or whatever.
Yeah.
Or property, sorry.
Raoult's law depends on the actual vapor pressure above a solution. It is a colligative property. The actual vapor.
But it's not what we're talking about right now, right? I got confused.
Yeah.
I'm sorry.
No. It is. I mean, it is a colligative. I was going to look at freezing point depression or boiling point elevation, but Raoult's law is a colligative property because it doesn't. Okay. It doesn't depend on what's dissolved in the volatile liquid. It just depends on how much of it is there.
Right. Okay.
So the pressure of let's see. Say we have a liquid that's confined, and there's a measured pressure here. That pressure. I'm going to use the right value. Let's say this is liquid A. So the pressure A under these new conditions is related to the pressure of the pure substance.
Gotcha.
And it's related in terms of what's the mole fraction of A. So the mole fraction of A down here, as you add more soluble, non-volatile compound or element in the in A, you decrease its actual vapor pressure.
Got it.
And as the added amount S, as you add S, the fraction of A goes down. All right, so if you know the concentration in terms of moles, the fraction of S, then the mole fraction of A has to add up to 1. Now, if you know the concentration of this one, you can determine the concentration of that one, and that's the one that goes with the equation.
Okay.
Now, this is Raoult's law for a volatile liquid, and the solute is non-volatile. If you have two volatile liquids dissolved in one another, then you have to use the modified Raoult's law. And that expression would be the total pressure would be a combination. Say it's only two components. It's keep it simple.
Yeah.
Would be the pure vapor pressure of A and the pure vapor pressure of B. Then you would need the mole fraction of A.
Mhm.
Of course, if they're the only two components in there, then
Right.
this would be 1 minus that one, or this one would be 1 minus that one. And that's where you get the that diagram where we have fractions of A and fractions of B. And
Yeah.
this one might go that way, and this one might go this way.
Mhm.
And this is pure B, and this is pure A. The combination would be
I'm sorry. I was just confused on that in my head. I just had to ask. I'm sorry.
oh no, don't be sorry. This is a good topic to hit right now. That would be the ideal situation, where A and B do not interact at all. They're just dissolved in one another. You get this straight line between those 2 points. If A and B interact significantly, they attract one another, then you get a negative deviation. And it goes that direction, like that. If they repel one another, then you get a positive deviation. Okay? Well, this is a good topic to cover, believe me.
Okay, good.
Okay, so now we can go to another colligative property. Having to do with, let's see, boiling point. So if we're going to talk about boiling point, we can compare. Let's say we have these 3 solutions. .1 molal. Remember molal? Moles per kilogram.
Yeah.
Okay. Molal of let's say it's alcohol you can't drink. Methanol. It's kind of they put in aquavelva. Then let's say we have, here's another possibility. It's the same concentration of this salt in aqueous solution, and this is aqueous. And let's say we have this one of, how about potassium phosphate? Okay. Now, we want to know, how is the boiling point affected? And this is not quantitative. This is a qualitative expression. How is the boiling point affected here? Which one has the lowest boiling point? Which one has the highest boiling point? Well, you have to say, what happens when they go into solution? This one is still 0.1 mole because methanol does not break apart. Same number of moles goes in and stays in solution. When sodium chloride breaks up, it produces 2 moles of ions and is completely soluble. So its concentration is 0.2 mole. Okay? And this one, we have 1 phosphate, and this is completely soluble. 1 phosphate, 3 potassiums means 4 for every 1. So this one is 0.4. Oops. That's wrong. There we go. Now, say we're at 1 atmosphere and pure water boils at 100 degrees centigrade. Which one's going to have the boiling point that's closest to boiling point of water? The one with the smallest concentration of solute. And the one that's going to have the highest boiling point will be the one with the highest concentration of solutes. So this is our boiling point elevation. And if we were being quantitative about it, that temperature, that elevation, change in temperature from 100 to whatever, and that all depends on your solvent, right? It'll change with the solvent. Requires a proportionality constant of some kind for the boiling point of your solvent times the molality of your solute times the is it Van Hoff correction factor, I think. And this just means to the nearest rounding, this is a whole number. So if there's no breakup, that'll be 1. If there's 2 to 1, that'll be a 2. 4 to 1 would be a 4. And there you can calculate the actual elevation in boiling point temperature. Freezing point goes the other way. But actually what we're looking for is the absolute value. We don't care about the sign. Just want to know how much it changes. Okay, so we talked about Rayleigh law. We talked about boiling point elevation. We alluded to freezing point depression. There's one other one. And that's osmotic pressure. This was a little harder to grasp. And let's see if I have a sample in here that we can work with. I don't see one. Okay. Well, we'll just cover it briefly. Osmotic pressure. Let's see, did I put the formula in the useful information? I hope I did. don't see it. Well, be sure I get it right.
You'll find it once class is over. That's how it always happens.
Okay. Yeah, that I value is the Van Hoff index. That's why it's an I, the Van Hoff index. And okay, we use a large pi for osmotic pressure, and then we have the Van Hoff correction. Works for this one too. Then you have concentration. We could use a C, or we could use, let's use a big M, because concentration is in molarity. And then we have the R value, which is the universal gas constant, and the one that uses, since we're talking about pressure, the one that uses liter atmospheres per mole K. So that's our 0.08206. And then temperature. Now the temperature would have to be in Kelvin, because R is Kelvin. And we can see that the osmotic pressure increases as the molarity increases. And since the formula incorporates temperature in the calculation, we don't have to use molality, because the temperature is corrected for in the process or in the calculation. So molarity is more convenient anyway. So what does that mean by osmotic pressure? Well, let's see. Let's do the YouTube version. Okay, and we have a semi-permeable membrane here, and for our reference would be pure solvent, and for those in the biological sciences, that's always water. So if we put water on this side, and we put the aqueous solution on this side, the semi-permeable membrane will only allow water to pass. Actually, it allows gases too, if they're small enough. Most of them are, but for argument's sake, we're only concerned with water. And if we put them in here at the same level on either side, then to begin with, the pressures are the same. But very quickly, we find that across that membrane, let's blow up the membrane. There we go. We got lots of water molecules on this side. And we have fewer water molecules on this side. But the solute cannot cross the membrane, right? So the only way that equilibrium can be established, and equilibrium in this case is equal pressures on both sides. The only way that we can establish well, actually, they're not equal pressures. They're equal pressure now. The only way we can reestablish equilibrium is for water to cross the membrane. So water's going to go that way toward the hypertonic solution. Hypertonic, tonicity means amount of solute. So hyper is greater hypertonic. Water is hypotonic relative to the solution, and the solution is hypertonic relative to water. So back to the story. Water is going to move this way. So what's going to happen? You're going to move water this way, and nothing goes that way to replace it. So water is going to drop down to here, say, just for argument's sake, and that much water moved, so it doesn't necessarily have to be equal in volume, right? Because we know when you add a solvent together, the combined volume isn't necessarily the same. The summation volume isn't necessarily the same as the combined solution. But what happens is it keeps moving here until the pressure for the water to move that way is balanced by the difference in pressure between here and here. That's the osmotic pressure, the difference between those two. And it develops because you reach a certain point where the pressure here is sufficiently great to drive water back through at the same rate as it's coming this way. So that's where your equilibrium is, water movement across the membrane. Okay, that's osmosis. Now, you can artificially increase the pressure on this side. And if you increase it high enough, you can drive it down to here and up to here. Right? You increase the pressure and exceed the osmotic pressure of the solution, then you can start driving water back this way. That's called reverse osmosis. And it's one way to purify salt water. We did it on a small scale in the lab I used to work for. We had a system in a room because it's kind of noisy when the pump's running. And it produced reverse osmosis water. Now, it's not pure analytical grade water, but it's pretty good. And then we piped it into the lab in plastic pipe. And then we ran the reverse osmosis water through our polisher, which is a series of filters. We had an ion exchange filter, which would replace all the ions with protons or hydroxyls. Takes all the ions out. Then we would have activated carbon filter that would take all the organics, because the ion exchange filter won't handle the organics. And then some of us, depending on the lab, if they were concerned with pyrolysis, that is, infection agents that could cause inflammation, they would have introduced an ultraviolet lamp that would shine on the water as it passed by and kill any bugs that made it through, including viruses. So it had to be a pretty strong lamp at the right wavelength. Okay, so those are the colligative properties. Let's see, I get a move on it here. Let's talk about entropy a little bit. Suppose, well, I'm going to need that. Entropy. The symbol is S, big S. Of course, it doesn't mean anything by itself. It has to be measured in reference to something. And actually, it's measured in reference to absolute zero. A perfect crystal at absolute zero is zero entropy. So you're actually dealing with a change in entropy in our world. So let me give you this example. Let's say we have, oh, okay. Then we got a fuel cell that combines oxygen and hydrogen to make water and electricity. Let's see, this is going to be a gas because that happens at a pretty high temperature. Balance the equation. Okay, we need two oxygens. Now we need 4 hydrogens. There we go. So now our equation is balanced. And we want to say something about if we're watching the reaction go from left to right, of course, what can we say about the sign on delta S? How does entropy change in this case? Well, you look at the amount of disorder, right? That's a simplistic view, but useful sometimes. The amount of disorder, right? And the amount of disorder where gases are concerned is, look at the coefficients. So we have 1 mole here, 2 moles there, that's 3 total, right? And we're talking about this reaction occurring in the same volume before and after. So if we go from 3 moles here to 2 moles here, what's happened to the level of disorder? Right? The level of disorder has decreased from 3 moles in that space to 2 moles in that space. So the sign on delta S would be negative. Of course, if we flip the reaction around, say we were electrolyzing water, right? Run a direct current through it and bust it apart into hydrogen and oxygen. It's really easy to do. Low voltage, right? 9-volt battery. Just drop a little lemon juice in a glass of water, preferably pure water, if you can get it. Distill water out of a jug. And then take a 9-volt battery and drop it in there. And before long, you'll start seeing bubbles form at the electrodes. One of them's hydrogen, one of them's oxygen. So the answer here is the entropy going that way decreases. The entropy going the other way would increase. Let's go from 2 to 3. Let's use a little electrochemistry here. If we're going from here to here, what's happening to the oxidation states of the oxygen and hydrogen? In this case, both of them are changing because that one's 0 and that one's 0, and in a compound, they can't be 0. So this one is a 2 minus, and this one is a 1 plus. This one's a 0, and that one's a 0. So going from this hydrogen over here, we're actually gaining electrons. And for our argument's sake, it doesn't matter how many. It just gains electrons. From this one to this one, it's a loss of electrons. Right? So if we've got a 9-volt battery, and we drop it in water, let's see, I think the small side here is the negative side. Let me see. I'll be right back. Here we go. Here's a 9-volt battery. Yeah. Nope. The small one is positive. And the big one is the negative. Okay, what does that mean? That means electrons are exiting that port, electrons are entering this one. So it's going from here to here. Right? So what does that mean? That means this side is the anode, because the anode oxidizes and releases electrons. Right? So water is losing electrons at that point. Electrons are being stripped off of the water to make oxygen. So this one, it produces oxygen. That means the other one has to produce hydrogen. So the positive electrode produces hydrogen, negative electrode produces oxygen. All right. Don't need that anymore. Maybe not. Keep it handy just in case. All right. Let's see if there needs to be anything more said about entropy. We got 45 minutes. If I'm not finished, I'll just keep talking when the time's up, and because I'm going to cover every topic that I want to, and it'll be recorded. Let's say we have let's do this one. Say we want to find the pH of a solution that could possibly be a buffer. Let's see if it is first. 0.6 molar nitrous acid. 0.6 molar nitrous acid. 2. Okay. And 0.3 molar sodium nitrite, I think. Yeah. Okay. Everybody knows sodium nitrite. They used to load up your hams with it because it would kill the bugs. It would keep the meat from spoiling. And of course the sodium added flavor. And it cured the meat faster than sticking it in a smokehouse. It's quicker and cheaper to pump it full of solutions. Anyway, we're going to combine this acid and that salt of the acid. Now, do we have a candidate for a buffer? That's the question first. Well, let's see. If we go from here to here, all right, that means this is the acid, this is the conjugate base. All right, do we have that possibility up here? Well, of course, this reaction is that by itself. But what we want to do is balance the amount of this with half of that, right? Because of Henderson-Hasselbalch equation says the pH is equal to the pKa plus the common log of the concentration of nitrate divided by the concentration of the acid. Oops. There we go. And the buffer zone is where this one equals that one. So that means that that one has to equal that one. Why? Because 1 divided by 1, or equals divided by equals, is 1. And the log of 1 is 0. So that would make this one 0, and those would be equal. You'd be in the middle of the buffer zone. So that one has to be equal to that one. All right. How do we get there? Well, in order to get there, you need you would need equal amounts of this one and that one, right? So this one isn't, strictly speaking, right in the middle of the buffer zone. It's going to be a different pH than you would expect for the perfect buffer. The question is, what is the pH? Well, we can use this equation because we're given this value. Well, I haven't given it to you yet, but I will. 4.46 times 10 to the minus 4th is Ka. Ka equals 4.46 times 10 to the minus, did I say 5? No, 4, excuse me. 4. Right? And we know the concentrations. If we have equal volumes of these two, let's just make something up. Say we put 1 liter of that and 1 liter of that. So 2 liters would decrease this one to 0.3, and 2 liters would decrease that one to 0.15, right? But what does that do to the ratio? Well, the ratio of 0.6 to 0.3, this is the acid, and there's your conjugate base. Oops, wrong direction, sorry. 0.3 divided by 0.6 would be the ratio here separately. But when you combine them, what happens to the ratio? Well, it goes to 0.15 and 0.3. No difference. Didn't change. As long as they're equal volumes, then we can use these values. Or you can use the others. I mean, if it messes with your head, just use the actual concentrations. All right. So now we've got those.
Sorry, I must have lost you.
Oh, that's all right. That's all right. I set the, I disabled the waiting room so you can come back in at will.
Okay, perfect.
So now we need to know what's pKa, because to find out the pH, we have that. Now we need this. So the pKa would be the negative log of that, right? Negative log of that would be whatever that happens to be. Let's see, so I don't have to whip out my calculator. Would be 3.35. So now all we need is the ratio of this to this, which would be 0.5, and the log base 10 of 0.5 is actually a negative value. Let me see what it is. I'm gonna have to calculate after all. So 0.5 and the log of that minus 0.30 minus 0.30. So that will be 3.05. So we're probably still in the buffer zone. Oh, I forgot to mention. I just kind of glossed over it. In order for this to be a buffer, what else do we have to have? That has to be a weak acid. And this proves it. Right? If that were HNO3 with sodium nitrate, you wouldn't have a buffer. You'd have a titration, but you wouldn't have a buffer. Okay, so 3.05 would be that one for this situation. Now, if you're so inclined, you can write out the equation and do an ice table, but I think we've already proved in PowerPoint slides and presentation and in working problems that if the conditions are right, Henderson-Hasselbalch is much faster and it gets you the same answer. Okay, now let's flip things around. We're going to calculate the Ka if we're given this data. Say we have, here's our acid, right, in an aqueous solution. And we're not making a buffer this time. Oh, it's 0.00796. So it's very dilute. Now, what do we know about let's see, it's iodate, and it's oxygen, so we don't say hydro. Iodic acid. What do we say about that? Well, the pH, we're also given the pH of 2.12. pH 2.12. Okay. Maybe this is a weak acid, right? Because if you got that concentration, what would the pH be? Let's just do what if. If this were a strong acid, what would the pH be? Right? You take the molarity here, since this is one hydrogen for that molarity, this would also be the concentration of hydrogen ions. So 7.96 times 10 to the minus 3, negative log of that. Let's just see what it would be. 7.96 exponent, change the sign, and then we'll take the log of that and then change the sign. If that were a strong acid, it would be 2.10 pH. It is a strong acid. Has to be a strong acid. We're pretty close. All right. So let's see. We don't need this. So what we're going to do is take that pH, and we're going to say, with that pH, what is the hydrogen ion concentration? Because the reaction, the question is, what's the Ka for this compound? Right. So we need the reaction, the dissociation of this compound in aqueous solution yields that plus that. Those are aqueous. Then we need an ice table. Okay, our initial concentration here is 0.00796, and that's 0, and that's 0. So, okay. So what is this? Well, we need to focus on the information we have, and the information is pH. We can calculate what this is from that. We just need to take the anti-log of the negative 2.12. So it would be 10 to the minus 2.12 equals what? Let's see. So I don't have to drag out my calculator. It's 759 10 minus 3. So now we're going to lose that much since it's 1 to 1. We're going to lose this much and gain this much. Okay. These are obvious. They're going to be those values as equilibrium. this one, we need to subtract that one from that value. Right? So we take, let's see, there we go. So now we can write our equilibrium expression. Ka equals this one times that one, and this one, and they're all coefficients of 1. So we just plug in the values. 7.59 times 10 to the minus 3 twice, right? Squared. And then divided by this one. And that should come out to 0.16. So it's not technically a strong acid, but it's got a pretty good K value. Right? There's a substantial amount of this that converts 16% of it at that concentration converts into protons and iodate ions. So, well, that's the answer. There's your K value. All right, let's see what other trouble I can get into. Just close that up. All right, so we got covered those. Suppose, let's see, I don't know if I have the information here to do this. I'll just use this one. Suppose we have a solution of that. Okay. Phosphoric acid. Now, phosphoric acid is a weak acid by our definition, but it can generate 3 protons. It can generate 3 protons, but how does it do it? Well, the first proton comes off with a K value of, I'm just going to use the powers of 10 because that will solve the problem for us. 10 to the minus 3. The second proton comes off 10 to the minus 8, I believe. We did these in lecture. And this is 10 to the minus 13. All right, what does that mean? That means that this proton is more dissociable than that one, right? By 5 orders of magnitude. And this one is 5 orders of magnitude weaker than that one, right? So the strongest proton of all is the first one. So if I give you a concentration, let's just say it's half molar. What's the dominant species in that solution? Well, let's see. This species would be derived from HPO4 minus. This one would be derived from this one. And this one would be derived from that compound, right? Because it would yield the protons, 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 right? So for this one, the dominant species would still be that one. And for this one, and since it's that one, then it would also mean that this one is the dominant species, right? But this one is the dominant species here because it's only 1/1000th dissociated. So what's the dominant species in that solution? That one. Now, which one determines the pH of the solution? That one. Because even if you produce some of that, you're not going to produce anything that significantly impact the numbers of these. And that one won't impact this one won't impact that one. That determines the pH. Okay. Let's see. Wet my whistle here. We got another 19 minutes, it looks like. I want to see if there's anything that I haven't covered. Here's one. Yeah, let's look at this one for just a second. Say we have, remember our reaction energy diagram. Let's say I give you these four to choose from. That one, that one, that one, that one. And this is progress. And this is all energy. These are different reactions, but I'm going to ask you to choose from among them. So this one starts out really low, huge activation energy, and then it settles down about halfway. Then this one starts off high. Well, middle. Produces a substantial activation energy for that low. This one starts off low and goes high. But it pretty much stays up there. And this one starts off in the middle with a lower activation energy. And okay. I know that looks like it can be confusing. The question is, what are the differences in these diagrams in terms of both their thermodynamic properties and their kinetics? Those are two different things, but we should be able to gather that from one of these. If we say thermodynamically favored, right, what we mean is the reaction is exothermic, right, because it gives up energy. And if it's thermodynamically favored, then it would have to be one of these. Right? Start high, end low, that gives up energy. Okay. That would be thermodynamically favored, both of these. Equals exothermic. How about the kinetics of the reaction? Which one runs faster, which ones run slower? The reactions that run faster are the ones with the smallest activation energy. So let's look at activation energies here. Activation energy here is huge. Activation energy here is huge. Right? So this is kinetically unfavored, these two. What about these two? Do they have the same activation energy? Well, no. The activation energy here is right there. And the activation energy here is right there, smaller. Okay? So if we were looking for the profile that was both thermodynamically favored and kinetically favored, this one. Yeah. But while we're here, this would be our choice if we were trying to make money at a reaction. This one will be thermodynamically favored, but kinetically unfavored, because the activation energy is substantial. These guys, all these three, are kinetically unfavored. All right. That's enough said about that. Okay. Mark that off the list. How about, say you're given this information. We're going to talk about kinetics again. Okay. So let's say we have some reaction, doesn't matter what it is really, it goes to product. Right? So, and we're told that the reaction is second order. So the rate is equal to our K value times A to the second power. Okay? Second order. And we're told the rate constant, actually we're given that information, 0.0482. 0.0482 is our rate constant. Okay, so that's this. And we're starting at 0.379. So our A 0 equals 0.379, looks like. 379. Yep. Okay, we're told it's second order. We're given all this information. Question is, what's the concentration after 2 minutes? So delta T is 2 minutes. Okay, let's step back and look at the information. Second order, if we got time that's being determined, we can't use the differential rate equation. We need the integrated rate equation. So the integrated rate equation for second order compares what? It compares time to the inverse of the concentration. So that means that the inverse of the concentration at any time t is equal to the K value times the time plus 1 over the initial concentration. Okay? So, do we have enough information now? We know this. Except the units are wrong. Right? That's seconds. This is minutes. So 2 times 60 is 120, right? 120 seconds. Okay, we know the K. We're given the K. So we can calculate A. What's the concentration? All you have to do is just plug this one in here. Plug this one in here. Plug that one in there. Solve for that one. When you resolve this one, you have to take the inverse of it to get the A. Don't forget to do that. Okay? Over here, you take the inverse of that value. Then you multiply these two together, add them together. Then you take the inverse of that whole term to get A. I'm just saving time. I'm telling you how to do it. You can do it at your leisure. All right. Let's see. I want to be sure I cover all the topics. All right. I hate to do this, but nature calls. So I'm going to pause the video and come back in 3 minutes. Okay, I'm back. Let's see. Let me check. I got one here that uses Clausius-Clapeyron equation. I'll see if I've included that in here, because that's not one that most people have memorized. I think that's it. No, that's not it. Well, if that problem shows up, I'll put the equation in the problem, embedded in the problem. So let's say we have, this one is really, we could use any equation and any law that we wanted to illustrate how to interpret data. So let's say we have the Clausius-Clapeyron equation, and it says the natural log of the vapor pressure is equal to the negative enthalpy of vaporization. How much heat is required per mole to vaporize the liquid into a gas? And then the universal gas equation, gas constant, excuse me. And then you times 1 over the Kelvin temperature. And then we have another factor out here that we're going to call beta. Okay. Now, when you see equations like this, the first thing that my mind goes to is, does that look like a straight line? And most of the good ones do have a straight line version. And this one does. There's your Y. There's your M. There's your X. And there's your B. Y equals mx plus b. Okay, now we can draw some conclusions. How would we, what data would we plot if we were trying to get at that value? Right? We wanted to determine the slope of a straight line. We got to plot x values against y values, right? So you would plot the x values here, 1 over t, against the natural log of the vapor pressure. Right? So at different temperatures, you would measure the vapor pressure. Then you would take the natural log of the vapor pressure and the inverse of the t and plot them together. And they would give you a negative slope, right? Negative slope. And this slope would be the negative delta H, divided by R, excuse me. So if that slope is the value equal to this, then whatever this value is, multiply it times R, change the sign, and you got your delta H. Okay? Okay. Let's see. Oh. Solubility. We haven't talked about solubility products yet either. Okay, let's say we have this compound. And we're going to put it in solution. And let's see, we need 2 fluoride ions. There's your balanced expression for the solubility of calcium fluoride. So what's the solubility product mean? Well, the solubility product is an equilibrium constant. And it's derived from this equation using the rules such that if we say that concentration times that concentration squared divided by this concentration equals the solubility product. But we know that solids don't count. So in the case of solubility of a solid, this one never counts. So that's why they call it the solubility product. It's always the product of that times that to the power. Okay. Now let's see, we'll give them some more information. The KSP, solubility product, we're given that. 3.5 times 10 to the minus 11. Okay. And we're asked, what is the molar solubility of this compound? Right. How many moles of that will dissolve in a liter of water? Okay. So this is our expression, and if we put it in the form of an ice table, then we know that concentration here doesn't matter. Concentration here is 0 to begin with, and then this is going to produce the same number of moles as that. So if we choose S value here in terms of that one, then if we solve for S, we actually get the molar solubility of that because they're 1 to 1. Okay? So how many of this does it produce? Well, for every one of those, it produces 2 of those. Right? Okay. So we might lose that much here, which goes back to what I was saying, choosing S correctly. That means that we have, at equilibrium, we have S and 2S. That means that this expression becomes S here and 2S here, which means 4S squared, right? 4S squared times S is 4S cubed. So the KSP, 3.5 times 10 to the minus 11 equals 4S cubed. Solve for S, and you got your molar solubility. Okay, I don't need to solve it for you because that's all the thinking is done now. From here on out, it's just crunching numbers. And anybody should be able to do that. Plus, we're running out of time. All right. So there we've touched on solubility. Let's see.
Hey, Dr. Black, I hate
Yes.
to do this, but I'm going to have to hop off here.
That's fine.
So anything, are you going to post, you're going to post this one today or soon?
Oh, yeah. Yeah.
Okay.
I'll get this one done probably. Let's give myself some time in case I have some snafus. Maybe 3 o'clock. I should have.
Okay. No rush. I just didn't want you to think I wasn't going to like listen or watch the rest of it after I get off here. So.
Okay. Now, before you go, you still there?
Yeah. Yeah.
I wasn't paying attention. I only have you and Kessa showed up. Did you see anybody else?
I didn't.
Okay. I don't want to miss somebody by accident.
Yeah. No, I didn't see anybody else pop up. I'm sorry.
Okay, that's fine. You can go now.
Okay. All right. See you later.
Bye-bye.
All right, bye.
Okay, so I'll continue on alone. And what I'd like to do is I'm going to present this problem. We've got the actually, this goes back to Rayo's law. We've got water at 23 degrees, has a vapor pressure, pure water has a vapor pressure of 21.1 millimeters of mercury. But what we're going to do is in that pure water, we're going to add 8.55 grams of sucrose. 8.55 grams of sucrose, table sugar. And we're going to add that to 17.6 grams of water. Let's see, let me give you the molar mass here is 342.0 grams per mole. And you ought to remember water. Right? Water would be, but we can round it off, 18 grams per mole. Actually, it's 18.02. What's the vapor pressure of the solution? Okay. What are we basing our vapor pressure on? On the solvent, water. So the vapor pressure is going to be depressed by the addition of a non-volatile solute. That means the ideal Rayo's law is in effect here, which is what? The actual pressure is equal to the pure pressure times the mole fraction of the solvent. Okay? So we got to find out what the mole fraction is. We already know what this is, then we can calculate. So our journey now is to find out what's the mole fraction of water. All right. What do we mean by mole fraction? Well, it's the number of moles, in this case, the number of moles of water per moles of sucrose plus moles of water. Right? It's the number of moles of water in the total number of moles. All right, so how many moles of water do we have? Well, we got to change 17.6 grams into moles. So we got to count some grams, moles. That's 18 and 1 here. So 18 into 17.6 is 0.978. That's water. Now we need to know number of moles of sucrose. 8.55 grams. Convert that to moles. We have 342. And that's going to be 2.5 times 10 to the minus 2. Sucrose. Okay? So, I need to make some more room here. Let's do this. We don't need the temperature because it's not changing. So now we need to put moles of water as the final pressure is equal to the mole fraction. Moles of water, 0.978, and then 2.50 times 10 to the minus 2. Is that what I said? Just check myself. Yep. Plus 0.978. And that's times the pure vapor pressure. Gotcha. All right. So, now it's just number crunching. Just add those two together, divide it into that, times this, and you get a value. Okay? Like I said before, I'm conserving time. Number crunching is not part of the job when we're short on time. If we have plenty of time, if I had plenty of time, we crunch the numbers. Okay. Let's take this theoretical problem. We'll talk about Gibbs free energy and its relationship to the value of K. Right? So what is the relationship of Gibbs free energy to K? Minus RT log K. Okay? That's just it. Now, let me use this one. That one's getting tired. What happens to K as delta G changes? Well, let's look at it this way. What does a positive delta G mean? A positive delta G means non-spontaneous. Right? And a negative means spontaneous. Okay. So let's say we want to find what would the K look like with a spontaneous reaction. So we need to make this one negative, right? So what would K have to be to make that one negative? Well, see this negative out in front? That means this entire expression has to be positive. So what's the nature of, well, the temperature, of course. Let's assume we hold the temperature constant. We don't change the temperature. And R is a constant. So we're only focused on changing the K for any given reaction. or maybe several different reactions, looking for K that we'd like. So what do we need for K to be positive? I mean, for this expression to be positive. Well, we can suppose, right? Natural log is what? It's base E. Right? So, what would give us a zero value? Right? Because zero, if we know what gives us a zero, then we can make some predictions on what would give us a positive E, a positive log, or a negative log. Right? So if K happens to be equal to E, then E to what power equals K? Well, actually, E to what power equals E? E to the 1 power, right? So K would be 1. If K were 1, then the log of that expression would be 0. If K is equal to 1, that's equal to 0. What happens to that expression if K is less than 1? K is negative. Well, what would we have to do to E to take the logarithm of it to make it that? Well, the value K would have to be, well, the natural log of K then would be positive. Would be greater than 1. Would it? No, sorry, other way around. If K is less than 1, then the natural log is also less than 1. That means that if K is greater than 1, the natural log of K is greater than 1, and that gives us a negative value. So only for K is greater than 1 can we expect delta G to be negative. All right. Let me just do a quick calculation to see if that's right. I think it's right. So if K is greater than 1, let's say K is 2. I'll take the natural log of it. Yep, that's a positive value. Let's say K is negative 0.5. Let's not go too extreme. Oops, let's go negative 0.5, negative. Take the natural log. Can't do it. Needs to be smaller than that. Let's say 0.005. No, that doesn't work either. Less than 1. Not 0, less than 1, excuse me. Not a negative number. Less than 1. So 0.5 log is a negative number. Yeah. Okay. So less than 1, 0.999999 is a negative number. Okay. I just want to confirm for myself that the natural logs do work that way. If K is greater than 1, you have a positive log or negative expression that I erased. In K is less than 1, you have a negative expression which gives you a positive delta G. Okay, let's get back to the other discussions. All right. Let's stay on delta G's. Let's say we have delta H's and delta S's for different reactions, or for the same reaction for that matter, because it will change with temperature. And let's say we have a negative value here, positive there. And then we have a, like that. So those are all four combinations that would fit into this expression that gives free energy equation. Okay? So we want to know which one of these would be spontaneous at any temperature. So any temperature, what would give us a spontaneous reaction? Right. So this has to be negative for spontaneous, right? That means that the sum of these two has to be negative. And that means that if the temperature is allowed to change, sky's the limit, then that means that the temperature influence on delta S cannot make it positive. Right? So delta S, to do that, to keep this negative, delta S would have to be positive. And delta H would have to be negative. If this is negative and that's positive, then you've got two negatives, always negative. Okay? That means this one. Okay? What if they're all negative? Okay? Under what temperature regime, because we know now the temperature is going to have an impact, right? Because if the temperature is large enough, a negative times a negative makes it more positive than that negative, right? So for very, very large values of temperature, that makes it non-spontaneous. So this would, large T, delta G would be positive. So we need small t for delta G to be negative. A small t would minimize this value and keep that one negative. I mean, keep the expression negative. Okay? Okay, another what if. What if this one is positive? Let's see. We did that one already. What if they're both positive? If they're both positive, right, we can't do anything about that one unless we assume that the delta H is fairly constant over a wide temperature range. Then we have to do that. Under what temperature regime would this still be negative? Right? If that's positive, wait a minute, if that's positive and delta S is positive, then T would have to be a large temperature to make this negative. So large T there. What did I say before? Oh, both of them were negative before. So under positive, positive, a large T gives you spontaneity. Let's go back. Let's say both of them are negative. If both of them are negative, then a small t, if I said large T before, I was wrong. A small t under these conditions would minimize the positive aggregate here and keep this one negative overall. Now, what if this were positive and that's negative. Under what conditions would temperature regime would you have a negative? Well, if this is a positive, it doesn't matter what the temperature is, right? Because we're starting at 0, so any temperature is going to be a positive value in K. So a negative times a negative is positive. All temperature regimes are non-spontaneous. But if we flip the reaction around, go the other direction, that reverses these. And now all temperatures give us spontaneity. Okay? That's all I have to say about that. Forrest Gump. Okay. Let's see. Let's try a method of initial rates. And we're only going to work on the order for one of the components. Okay, we're not going to mess with multiples, doing all. So let's say here's our data. All right, so we have A, concentration of A. Oop, that one's crapping out on me. I better get rid of it. Let's see if this one still works. Concentration of A, concentration of B, concentration of C, and then the rate. Okay? Yeah, that one's doing it too. Let's see if we've got anything left in the box here. Oops. I have to find it. Where is it? This one. All right. And we got 4 experiments. And this one is 0.10. And then C is 0.10, 0.2, 0.2. There you go. And initial rates here in molarity per minute. Right. The first one is 3 times 10 to the third, 6 times 10 to the third, 2.4 times 10 to the fourth, and 2.4 times 10 to the fourth. There we go. Okay, so we have a reaction here, and these are the reactants. Reactant A plus B plus C. Right. You don't need to know the balanced equation. The expression then would be the rate is equal to a K value times A to a power times B to a power times C to a power. Okay, the order of each one. So let's say let's pick B. We want to know what's N. What's the order of B? So what you want to do, this kind of gets in the way, but there's A, there's B, there's C. You want to look at 2 reactions where B changes in concentration, but A and C do not. Right? So B changes from here to here. So which one of these does A and C not change? Well, they change there. Here. So they don't change there, but no, that's not right. That's not right. You want them not to change this direction. So that changes from there to there. Give me a second. So we got to have one of these compared with one of these because the B changes. So which one of these doesn't change? That one changes. These two don't change. Here we go. See what I was looking for? This one changes from here to here, but this one stays the same, and this one stays the same. Okay? So now what do? Well, you ratio this rate expression to that rate expression. So rather than erase that, let me see if I can pull out another whiteboard. Yeah, that's visible. Okay, so we want the rate. Let's see, this is reaction number 2. This is experiment number 4. Experiment 2, experiment 4. So how do we choose which one goes on top? Well, it's best to choose the one where you have the larger value on top for the rate, so that you get a whole number. So we're going to do rate 4 divided by rate 2. Right. So what's that expression? Right. So we have A to the M, A to the N. We have B. Let's put values. Well, no, let me go ahead. And then C. And the B. There we go. So we're ratioing this rate expression to that rate expression. Right? And that's algebra. I mean, it's valid. Because this is equal to that, so if we divide these two, we have to divide those two. All right, so now what can we say here? We know that this one is going to be equal to that one. We designed it that way. This one's going to be equal to that one. So it goes away. Now what we have to do is put the rate value in for 4, which is 2.4 times 10 to the 4th. And for 2 is 6 times 10 to the 3rd. Then we can divide the actual values of B, which would be 0.2. Remember, we did this one first. 0.2 to the N divided by 0.1 to the N. Okay. Now, what's this expression? If you divide two numbers and both of them are to the same power, it's the same thing as the division to that power. Okay? So what do we get here? Well, let's see. Should be able to do this in my head. If we want to change this one to 10 to the 3rd, it would be 24 times 10 to the 3rd, right? As we take one of those 10s and put it over here. So instead of 2.4, now it's 24. So that's divided by 6.0 to the 3rd, right? 10 to the 3rds cancel. So 6 into 24 is what? 4. So this expression is the whole number 4. This expression is 0.1 into 0.2, which is 2, right? To the n power. So what does n have to be to make 4? 2 to what power gives 4? 2. N equals 2. All right? That's the method of initial rates. You can do that for all 3 of them. I mean, if the question is asked, you can do it for all 3. You just pick a different set of equations. If we were going to do A, which ones would work? If we were going to look for A, we would want these 2 to not change, but A to change. So these 2 changes. How about this one and this one? No. We want A to not change. No, we want A to change, B and C to not change. So A changes from here or here to there. So this has to be one of them. Right? So where else do we have 0.2 and 0.2? This one. Right? Those don't change. This one does. So we would use 3 and 4 to find out what A is. Okay? And if you want to do C, I'll let you do that one. All right. Let me erase this one. The longer it stays on there, the deeper it sets. So we won't get rid of it quick. Put that back here. And pick this thing up. I keep knocking that on the floor. There we go. Okay. So I made my point with that one. Let's see what else I can find in here of interest. We've already covered those. All right. Let's do another buffer problem. Buffer problems are fun. Suppose you're given a buffer solution that's made with acetic acid and sodium acetate. So, acetic acid concentration is 0.1 molar. And let's see, we're also given the pKa 4.74, I believe. Yeah. And we also add to that C2H3O2 equals now I say we added 1 mole of this to a liter and 1 mole of that to a liter. And we're going to assume that the total volume is a liter. If we don't, then we messed up our volume. All right, so do we have a buffer here? Well, actually, yes, we do. If we have that concentration of this one and that concentration of this one, we have a perfect buffer. And the pH of this buffer is 4.74. Why? because Henderson-Hasselbalch said if these two are equal, the log term goes to 0. And then the pKa and the pH are the same, right smack dab middle in the buffer region. Okay? But here's what we're going to do. We're going to complicate it. Let's say we add 0.01 moles of sodium hydroxide. So we're going to add 0.01 mole of sodium hydroxide to that buffer. How much will the pH change? Not what is the pH, just how much will it change? By how many units will the pH change, and what direction? Well, we can qualitatively say, if we're going to add base to it, the pH is going to increase, right? Not by much, because we're in the buffer, but it will increase some, right? So the change is going to be positive. That's just a check, right? If you come out with a negative change, you know you made a boo-boo somewhere. You need to go back and check your numbers. Okay. All right. So what reaction are we conducting here? We're reacting this one, which is the weak acid, with that one. So let's put up our ice table. I have to erase this, sorry. I don't want to pull out that other one. So let's say, here's the reaction that we're talking about. C2H3O2 plus hydroxyls yields C2H3O2 minus plus water. And we don't need to include water because it's pure liquid. It doesn't enter into the equilibrium expression, right? We're still at equilibrium, right? I warned you, when we started talking about equilibrium, we'd never stop. So what's our initial concentration? The initial concentration of this was 0.100, right? And the initial concentration of this is 0.01 mole. Why? Because we produced a liter of solution to begin with, and now we're adding 0.01 mole of this to a liter. And we're saying that, for argument's sake, the volume doesn't change. Oh, and we're also starting out with 0.100. There we go. Now we're going to get a change in an equilibrium situation. So, which way is this thing going to change? Well, when you add this to it, it's going to, hydroxyls are extremely good bases. That is, they latch onto protons with tenacity. So all of this is going to be consumed as it extracts a proton from that weak acid. This is a stronger base than this is a weak acid. The strength of this is much stronger than that. So that means we're going to lose all of this. Okay? Down to 0. So when that happens, we're going to, it's 1-to-1, one of these, we're going to lose that much. And it's going to show up on the other side. Okay? Now, what's the result? 0.101. 0.101 molar of the conjugate base, And the amount of acid that's left is 0.990. Let's see, 0.099. Right? Oh, no, sorry. Well, there's nobody over there to tell me I'm wrong. But I am. I'm wrong on both of them. No, wait a minute. Let me be sure. This is 1, 2, 1, 2. This is 1, 1, 0. There we go. That's right. And this is 2 decimal places, 2 decimal places. So this is 0.09. Okay, so now that we know what the equilibrium concentrations of the acid and the conjugate base are, we can use Henderson-Hasselbalch to solve for the pH. So now the pH is 4.74 plus the log of conjugate base divided by the weak acid. Right? But the question is, how much does the pH change? This will give you the actual pH, but how much it changes is right there. So all we need to do is say, the log of that value. Yeah. And divide by 0.09, which is 1.22. Take the log of it. There it is. And that is equal to 0. Let's see, 0.87 pH units. So the pH is only going to be 0.087 units higher than 4.74. So the pH will be 4.83. But if the question is, how much did it change? It's only this part of the expression that measures the change. Okay? All righty then. Close that up. Check that one off. All right, I'm already 45 minutes past. So let me try to make the most efficient use of time. Let's say oh, I already did that one. Good. So I can focus on this one. All right. Gibbs free energy again. Oh, I gotta make room. All right. So let's say we have what's the delta G for this reaction in gas into the all right. So the question is, what changes in conditions here will decrease delta G? We want this to decrease. What changes will decrease that value? Well, there are a number of approaches we could make here. We're not given any other information. So this is the actual delta G for the reaction. So it's not the delta G 0. Those are standard conditions. So what changes will decrease that value? The operative equation is this one. We can find out what that is if we know what this one is, and then we introduce this expression. Oops. Not time, it's temperature. And log Q. Now, why do we say log Q? Because if this is K, then it's at equilibrium, and the delta G for that reaction is 0. That's why our earlier expression for delta G 0 was in terms of log K. And we said delta G equals negative RT log K. Because if that's 0, and we move this one over here, it becomes a negative. That's where that expression comes from. This is the origin. This one only works if you're interested in the reaction not at equilibrium. Then what's the true delta G for that reaction under those conditions? All right.
Hello.
So these are all gases. So let's work it in terms of decreasing the partial pressure of each one of these and see what happens to delta G. What if we decrease the partial pressure of this one? What is the equilibrium expression for this one? Well, if we were interested in Q, we would write this. And it would be that one divided by this one times that one to the 1/2 power. There we go. Now we got something to work with. If we say that we decrease this one, right? If we decrease this one, what happens to Q? If we decrease this one, Q gets bigger, right? You make the denominator smaller, the quotient is bigger. So this one increases Q. Okay, now with an increased Q, we get a larger value here. A larger value for this term, because we're not changing the temperature. You get a larger value here which adds to that, which makes delta G bigger. So in that case, delta G increases. Okay? What does that mean? It becomes more positive. It's less likely to occur, right? It might still be spontaneous, don't get me wrong. It could be negative. But if we increase that value, then we are saying that we have reduced its spontaneity. What if we decrease this one? Same thing's going to happen. If we decrease this one, we're going to get the same result, right? Because it's in the denominator. It makes Q bigger. Now let's decrease this one. If we decrease that one, it makes Q smaller. So if we decrease into O partial pressure, then Q gets smaller, and it makes this one smaller. That makes the overall smaller because this term is decreasing. Doesn't have to subtract, but the expression itself makes the whole term smaller. So delta G now is going to get smaller. So if it was spontaneous before, it'll be more spontaneous now. All right, just out of just to drive this point home further, what if we stick a catalyst in there? What effect will it have on delta G? It says nothing about equilibrium, because that's what we're talking about. This is thermodynamics. It's equilibrium. Catalyst talks about kinetics. So it has nothing to say about this. It doesn't matter what you do with a catalyst. It does not affect this at all. All righty. Let's see. All right, I'm past noon. So let me pick one more and call it a day. Let's see. Oops. Do I want to do that? Or do I want to do this one? Okay, let's do this one. All right. This is a good real world. The kinetics of the metabolism of a drug in your system is monitored. So probably what they do is they give you a certain amount of the drug, and then they measure a product of the reaction in your urine, right? Because before they even give you the drug, they're going to characterize how it reacts in the body. Now we're just looking at kinetics. You know, how fast does it react in the body? So they know what the product is, and they can measure the kinetics based upon the appearance of this product, metabolic product. And they can relate that back by the balanced equation to how much of the drug is being consumed over time. Okay, so the drug is metabolized in first order reaction. So we know it's first order. Let's see, what did I do with my others? What did I do with my other markers? Here they are. Okay. All right, first order kinetics for the drug being metabolized. And we're saying that the drug goes to product. And that's probably picked up in your urine. And they can find out how much of the drug was metabolized by how much of it shows up over time. Okay, if it's first order, then what does that say about the reaction? Well, we could say the rate is equal to some K times the drug to first order. Right? We know that. But the next part of the question means that we can't use that because time is introduced. So we're saying that we're also given the half-life, T1/2 equals 4.12 days. Okay, so that drug lasts a good time in your system. Right? Well, when you get antibiotics, what do? They make you take, some of them they make you take twice a day, right? So the half-life is probably in the neighborhood of not 12 hours, it's probably closer to 8 hours, 6 or 8 hours half-life. So you take it often enough so it rise up to a level and you keep that level in your system, the antibiotic, until all the bugs are gone. Okay, back to the problem. So a first order half-life means what in terms of our equations? Well, the half-life then is equal to a first order half-life is equal to, I wrote that wrong, sorry. That's the half-life. And this K is equal to 0.693 divided by T1. There we go. Okay. So we can find out what K is, right off the bat. Just plug in the numbers. T1/2. Uh, 4.12 days. So K would be, let's go ahead and work this one out. I'll crunch the numbers in this case. 693, because I'm following through on it. So this is 0.1682 reciprocal days, because it's in the denominator. So there's your K. Is that useful? Well, it depends on what the question is. If the initial concentration of the drug is, or the initial amount is 100 milligrams, then after how long? How much remains after 30 days? So what's the operative equation here? Well, it's first order, and we don't need the differential anymore, so let me move that out. It's first order, so that means what? Zero order is straight concentration, First order is natural log. Second order is inverse. So the natural log expression is the one that holds here. The natural log of the concentration, well, we'll say A is the drug, equals a minus K times time, and we have the K, plus natural log of the initial concentration. All right. So, with this equation, what do we have so far? We've got the K right here. We've got the time there. We have the initial amount right here. Now, why is this not in concentration units? Because you're putting it in one person, and you're assuming that the amount of the person isn't changing. Right? So you can equate this amount to a concentration. Once you put 100 milligrams in them, then the denominator or the volume of the person doesn't change. So the amount is proportional to the concentration. That's why we can use 100 milligrams and not have to know how big the person is. And of course, the researchers want to know that. And they do eventually calculate dosage based on the size of the person and how fast it disappears. Right? And potential toxicities, but those are other issues. So we can say we can use 100 milligrams as our concentration. Right? It's kind of like the kinetics experiment we had earlier, where we equated absorbance to concentration. Absorbance is not concentration, but it's proportional to concentration, so we can use it. The absorbance of the blue dye, if you recall. Okay, so we've got this, we got that, we got that. We can solve for that. Okay, so let's just do it for fun. So the natural log of the concentration of the drug is equal to minus 0.1682, 0.1682, and this is in terms of days, so this is right, 30 days, plus the natural log of the initial concentration, which is 100. Okay, so now I'm going to have to erase them. Erase this. All right, so now let's resolve these expressions. I feel like crunching numbers now. Since there's no time constraint, 4.6052. 4.6052 for that expression. This one is 30 and 0.1682. Change the sign. Times. This is minus 5046. Minus 5.046. Plus that. So you got a negative and a positive. And let's say, add those together. So this is minus 0.44083. And that's the log of our drug concentration. So how do we find what A is? Well, A is equal to E to the minus 0.44083. Now, if I didn't make any mistakes, let's see. Let's see if I made a mistake. I need to take that value as is, as a power of E. So in my calculator, I need, where is it? Here it is. So that's equal to 0.644 milligrams. So in 30 days' time, this drug has gone from 100 milligrams down to 0.644 milligrams, or 644 micrograms. I don't think that's a therapeutic amount, do you? I guess it could be. Depends on the drug, right? But now we know how much is there after 30 days. All right. So that's it. That's the last of our encounters. Unless you call me up, we won't meet on Thursday. Thursday will just be the exam. I'd prefer that you get all your work in for Friday next week, or Friday this week. So I'll have time, particularly if you have lab reports to turn in. Those lab reports take a huge amount of time to grade. So the sooner you get them in, the better. If you don't have any grades showing in your My Grades in Blackboard, that means you've not turned them in. I never received them. So you need to try again or attach them to an email. If you got an email from me saying, I see the submission, but there's nothing there. Sometimes Blackboard does that. You think you submitted it, but there's nothing there. So I send you an email saying to that effect. And what I usually do is I delete that submission so you can submit again. And for insurance, it's probably a good idea if that occurs to attach your report to an email also, just to be sure that I get it. Well, that's all I had to say. The exam is 89 points. Let's see. Yeah, there's some 1s and 2s, 3s and 5s. Let's see, if you go any higher than that, number of points per question, depending on the difficulty. And then their bonus, you have 30 points worth of bonus. The answers are all multiple choice, but some require calculation. In this case, you don't have to show me the calculations. But the exam, of course, is like all the others. It's on Blackboard, and you have a time limit. I'm thinking that I gave you 2 hours for this one. Don't hold me to that. But I probably gave you 2 hours, just so you have plenty of time. You don't have to rush. And the grade is worth 20% of your final grade in CHEM102. I'm still missing some chapter tests too, also. So you need to get those in. Those are not a problem because they're graded by the system. Homework is not a problem because it's also graded by the system. I just need to put it into my spreadsheet to calculate your average. The one that really takes time is the lab reports. So get those in early, because if I run out of time and I can't grade them before the grades are due on Monday, then that's a 0. So don't push me to the limit. I might do like a mule and just sit down and not move. Okay, that's it. I'm going to try to have this one posted in Blackboard by 3 o'clock this afternoon. Bye-bye, and enjoyed it.